Log on, tune in, find out. Another good idea from Cambridge.
Schmeiser, who's going to talk on macroscopic limits and fluid-kinetic equations of relaxation, collision kernels, and mass conservation.
Thank you. I apologize for the long title. So, thank you very much for the invitation. I'm happy to be here. I talk actually on two different projects on similar equations. So this is why Jean Dolbeau's name appears twice here, because you have to read these two lines separately. So this is two projects where Jean and myself have both been involved in. The first one together with Peter Markovic and Dietmar Oelz, and the second one with Clément Moreau. And actually the second project is the more recent one, and it's the main reason for me to pick this subject. But about the first thing, I've never really given a talk, so I take the chance to also present these to you, although it's not as recent as the other. The problem is to the group of experts here simply explained. It's a rather straightforward kinetic model with a with two essential ingredients. One is a confining potential, which is given a steady state. So from that point of view, not so difficult situation. And the second ingredient is there was a stick. Is an energy profile. This function gamma here of one variable. These we want to prescribe, and we want to allow as much freedom as possible in this energy profile. And then the whole model is made mass conservative by choosing the chemical potential here as a function of the density, such that the collision operator preserves mass. Okay, and we're interested in Cauchy problems. We could do different kinds of space dimensions, but for the sake of this talk, I stay with physical R3. And the goals here are the standard ones. It's the macroscopic limit on the one hand, and time asymptotics decay to equilibrium on the other hand. And the first of these two projects is the macroscopic limit one, and then the more recent one is the analysis of the time asymptotics. And of course, there is a lot of work on both kinds of questions, and in the second one we are rather ambitious. We try to prove exponential convergence to equilibrium. So that's the question here. Yes, what else to be said here? Not much. So I will just give you a outline of what I want to talk about. First, I will shortly, because that most people will be able to do that by themselves, talk about the formal macroscopic limit, say a few words about that. Then I will give you a list of examples of this equilibrium energy profile, and I will tell about general assumptions. But so there is assumptions on these energy profiles which are rather technical, and I replace these assumptions by the list of examples so that you show what's included. Then I will talk a little bit about what you have to do to make the macroscopic limit rigorous, some estimates, and maybe a little unusual in this community is that I will, for getting the necessary compactness, I will use compensated compactness and not averaging lemmas. This was actually motivated by work of Thierry Goudon and Frédéric Poupeau. So it's very similar to that. Then comes the second part. Hypocoercivity is the fancy name for exponential convergence as t tends to infinity. And I will present to you an abstract framework for proving that, which we have developed recently. And in the end, I'll give you a few applications of that. So let's start with the formal macroscopic limit from before. You remember we had an epsilon squared in front of the time derivative, an epsilon in front of the transport operator, and 1 in front of the collision operator. So if you let epsilon tend to 0, the collision operator has to become 0. And that means, since we have this simple PGK form, that we immediately get that F has to have the form of an equilibrium distribution. And then if we work a little more, I don't want to go into details there. It's a little bit more involved than what we just heard in the talk before, because it's not a hydrodynamic limit in this case, it's a diffusion limit. The reason for that is that our equilibrium distribution function is an even function of velocity, so it has all the fluxes of the equilibrium distribution function vanish, and so we have to go, the evolution is 1 order slower in some sense, and so the limit is diffusive. And the interesting thing is here what you get is you expect the convection diffusion equation because you have this confining potential providing the convection. But the interesting thing is that we get a nonlinear diffusion, and this nonlinearity, nu of rho here, is actually determined by the choice of our equilibrium energy profile. And the computation is the following. When you're having your equilibrium profile, that determines how the chemical potential depends on the density by the requirement that the densities are the same here. And then if you have this mu bar, here's the formula for the diffusivity, which is actually the derivative of my nu of rho here. Okay. First, one formal question which arises is maybe I'd like to do the inverse. Maybe I have a nonlinear diffusion equation and I'd like to find the equilibrium profile gamma where this comes from, and actually it's possible to do that. That is the next. On the next slide, suppose you know the mu bar, right? That was the which basically is a simple computation from the nonlinearity in the macroscopic model to compute the mu bar, and you can invert it. Then you have from the equality of the densities, you can rewrite it in this form here. And now you notice that this can be seen as an integral equation for the energy profile of Abel type, actually. And Abel type integral equations are the nice ones, which you can invert. So you can solve this equation for gamma of E, and you get a formula here. So given the nonlinear diffusivity in the macroscopic equation, you can produce a kinetic model, which gives it. But actually, there's an interesting question. If you want to be rather general, the question is: do you really get a kinetic energy profile which satisfies the minimal requirements which you need? And one of the minimal requirements is that it's positive. And that question is not so easy to answer. In a paper a while ago with Clemens Fellner, I have worked on this question, but there is no conclusive answer. There is only some partial answers. For which nonlinearity in the diffusivity you can actually produce such an energy profile. I don't want to discuss it further here. Okay, and then the list of examples of energy profiles, and there are the obvious ones, which all of you like. The first is Maxwellian. Of course, Maxwellian gives in the case of gamma being an exponential, the whole equation becomes linear, and the result is, of course, a linear diffusion equation. So it's just the standard macroscopic Fokker-Planck equation in this case. However, what you can also get are the standard nonlinear diffusion models with a power loss, and depending on the power, you have to take very different forms of the equilibrium distribution. So if you take algebraic decaying equilibrium distributions, you get a fast diffusion equation, and you can get all exponents here between 0 and 1 by an appropriate choice of the exponent here. And you can also get porous medium equations, but here what you have to take is a energy profile which has a compact support. So you see only if the energy gets positive, it's 0. And what we can get here in 3D is the porous medium equations with exponents between 1 and 5/3. Okay. And finally, two more examples come from quantum physics, if you want. Fermi-Dirac or Bose-Einstein distributions. We can also deal with what the interesting thing with the Bose-Einstein distribution is that there is an upper bound for the macroscopic density where the diffusivity tends to 0. Okay. Otherwise, they are not so hard to deal with. I should point at the 0.3 porous medium. This is technically the hardest one to deal with because of because it is exactly 0 after a certain point, and that creates difficulties. However, what we do in this work is not to deal with these examples separately, but do one theory and have a set of assumptions on gamma, which includes all these cases. But to give you all these examples, this is rather technical, and I don't want to do that. So, however, we also need assumptions on the other. At least a few of these assumptions, which are the simple ones and which are the more obvious ones. So the energy profile needs to be non-negative, of course. It needs to be Lipschitz. It needs to be strictly decreasing on its support, but it's allowed that it has a compact support. It needs to decay fast enough such that the macroscopic energy is bounded, and then other technical assumptions. These are rather difficult to formulate, but replace them just by the list of examples if you want. For the initial data, we make a rather strong assumption, which is that it's bounded by a global equilibrium. I should have talked about global equilibrium maybe before. Global equilibria are distributions which are both in the kernel of the collision operator and of the transport operator. And the transport operator, including the confining potential, has its kernel is constituted by functions of the total energy. So if you have something which is both an equilibrium distribution and a function of the total energy like these here, then it's a global equilibrium. And we assume initial data to be bounded by this. And actually the interesting thing is that these inequalities are preserved by the flow of the kinetic equation. And also what we ask is that the potential is confining, and that's of course confining means roughly this, but what does it mean exactly? And it's formulated here. It has to be confining enough such that the total mass and total energy are bounded. Okay. So estimates. The first one I already mentioned as a maximum principle. So the bounds so between 0 and a global equilibrium, these are preserved. The second one is the more interesting one. There is a entropy or free energy. Physically is more free energy, but I call it entropy from a mathematical point of view. It's the total energy plus the entropy, and the entropy here you obtain by inverting the equilibrium distribution and taking a primitive of that, basically. And then you have the typical chains of inequalities. So the entropy decays in time. So it's at any time the entropy is smaller than the initial entropy, which is smaller than the entropy of this upper bound which we had, which is chosen such that the entropy is finite. And also the entropy decays, and there is an equilibrium distribution which has where the quasi-Fermi potential, the constant in there, is chosen such that the infinity has the same total mass as the solution, and that is always below the solution and bigger than minus infinity. So you have this typical chain of inequalities. And for the macroscopic limit, it's always interesting to look at the entropy dissipation, which I have written here. And just the integration of the typical entropy inequality also gives that this quantity is of the order epsilon squared. And as you see, in some way, this quantity measures distance between the distribution function and the equilibrium distribution. However, if you analyze this for the typical choices of gamma which we have, you see that the control of this distance here by this quantity is not very good one. It's not obvious to say that in any way, or you don't get the result as a consequence that in any norm the distance between f and the equilibrium distribution is order epsilon, which is what you would want. However, if you work, and now from this slide to the next, there is a lot of work involved. Actually, that's all the work basically there is to do in this problem. Is the following estimates here, that when you look at the macroscopic flux in the correct scaling, because you expect, as I said, the limiting flux, if you put the equilibrium distribution here is 0, so if you only see something if you divide by epsilon, you can write it in this way to see that it has to do with the difference between f and the equilibrium distribution. And the interesting thing is that although I said we do not have very good control of this difference to be order epsilon, we can still show that this macroscopic flux is bounded. And the same for the non-equilibrium contribution to the stress tensor. Okay, this would be without the gamma, this would be the stress tensor here, and the non-equilibrium distribution of the stress tensor, appropriately scaled again, is also bounded. And this is all the important estimates which you need, and that's the advantage of this compensated compactness approach, which I briefly will show you now. As I said, that we tried to do this was motivated by a paper by Thierry Gaudon and Frédéric Poupeau a while ago. So the idea is the following. You write down the mass conservation equation and the momentum balance equation. Okay, and if you write these two equations, forget these left-hand sides first. So this is the mass conservation equation, and this is the momentum balance equation. You see that the only quantities which come up, the only macroscopic quantities, are the density, of course, then the macroscopic flux, which I had introduced before, and this non-equilibrium part of the stress tensor, and you can write it in this way. And now if you reorder terms appropriately and you use in Tx space these two vector fields, capital U, capital V, this is actually rather standard to do it in this way, that you see you can have an equation for the divergence of the one and for the curl of the other. And the right-hand side of the one equation is 0. The right-hand side of the other equation can be seen to be pre-compact in H minus 1, right? We have boundedness of this in L2, so it's pre-compact in H minus 1. These we have nicely bounded. This is no problem at all. Also pre-compact in H minus 1. K was bounded in L2, so this is bounded in H minus 1. Also with the epsilon in front, it goes to 0, so it's also pre-compact in H minus 1, and the same holds for this term. We have boundedness of J time derivative. So that's good enough for applying the Dief-Kernel lemma. What you get is the scalar product of these two quantities, capital U, capital V, converges weakly to the product of the weak limits. So you have that rho has a weak limit, and U of rho has a weak limit, and what we know is that the product of the two converges weakly to the product of the two weak limits. Okay, that sounds like not too much at the moment. But now using properties of this function U of rho, and actually the only thing which we need is its strict monotonicity, then allows in a standard way by working with the Young measures with the Young measure of rho to prove strong convergence of rho, and that's all we need. So it's a rather standard application of the compensated compactness method, I would say. Here is also is the difference between the work of Gaudon and Poupeau. They used some convexity properties, but this is very similar in some way. Okay, and that's all there is to do basically. The rest is rather standard, passing to the limit, and then there is a rigorous macroscopic limit result under the assumption which I told you, where the assumptions now for this talk are: take one of the list out of the list of examples of the energy profiles, and take the appropriate assumptions for the confining potential and for the initial conditions. Then this works. Okay, so this was this first project, and now the second one. And here I start with something very very abstract actually. So compared to the talk before, first of all, I linearize at the moment, right? The basic approach is actually a linear approach. So we assume this compared to before is just the linearization of the equation before at equilibrium. So then this T is an abbreviation for the transport operator, and L is the linearized collision operator, where actually only the gain part something happens, right? Because it was just this BGK model. But now forget where it came from and say this is an abstract equation on a Hilbert space. Okay, we'll have to talk about what the Hilbert space is in the kinetic setting afterwards. But now just take it as abstract, and there's two abstract linear operators. We call one of them the transport operator and the other the collision operator, but that is just words at the moment because it's just an abstract problem. And we assume two things. First, we assume that the transport operator is a skew-symmetric operator, and we assume that the collision operator is a symmetric operator and that it is negative semi-definite. Note that we do not make any boundedness assumptions. So T and L could both be unbounded operators like it is the case in some kinetic models. Right? It's not, for L it's not the case in the model which we just considered, but for T it's always the case because there's differentiations. Okay? So these assumptions already are enough to get the H theorem, that where the entropy here is just the norm, the Hilbert space norm of F. By the skew symmetry, the part from the transport operator goes away, and this is just the negative semi-definiteness of L. Now, the idea is what, of course, the standard problem for inhomogeneous kinetic problems here is that this L is only negative semi-definite, so it only controls, this term only controls part of F, the microscopic part of the distribution function, but not the macroscopic part. So how can we ever get convergence to F equals 0, which is here the equilibrium? Okay, and in particular, how can we get exponential convergence? Because that's the hope. So because before I continue, I have to talk about a little bit about more properties of these operators here, because in this abstract framework I still have to relate it to the kinetic, and in particular what I'm interested in is again the macroscopic limit, because what I should say before that the strategy for getting this exponential convergence here is to combine microscopic and macroscopic information. So the microscopic information is just information on the collision operator, right? This negative semi-definiteness will have to be made more precise in basically a semi-coercivity, if you want. And the other information is macroscopic information. So I will assume that the macroscopic limit equation actually provides exponential convergence. That will be one of the results. And then the idea is to combine these two informations and to get for proving the exponential convergence. So first of all, I want to talk about the macroscopic limit again now in this abstract setting. And in an abstract setting, I cannot be sure in the beginning if the macroscopic limit is a hydrodynamic limit or a diffusive limit. So that means not knowing that, I allow for two different scalings here, either a diffusive or a convective scaling. Okay? And then I just start doing the asymptotics. I give a name to the rescaled fluctuation part. Did I mention that the projection, that P is the projection to the kernel of L? I should have said, did I have that somewhere? No, maybe not. I forgot to put it. So the P here is a projection. It's the orthogonal projection in the Hilbert space to the kernel of the collision operator. Okay? So roughly the idea will be, and we will make this precise in a moment, that LF equals 0 requires that F is in P of H in the projection of the Hilbert space. So then the fluctuation part is written here, appropriately rescaled. We expect it to be of the order 1 over epsilon, of the order epsilon. So we plug this into the equation and then write what I would call the conservation laws from kinetic side, but it just means apply the projection to the equations here. So I apply the projection, and the equation I get is this, using this non-fluctuation part. Since I assumed L symmetric, L commutes with the projection P, so LP is P, since LP is 0, PL is also 0, so the right-hand side goes away, and you just have contributions from the fluxes here. And now you see there's two options, and it depends on this, what this combination PTP here does. If this is non-zero, then that's the convective situation. This is basically the fluxes of the equilibrium distribution. Okay, so then you are in the if this is non-zero, you are in the convective situation. You have to choose alpha equal 1, and then this would be the limit. You just drop this term in the limit, and that's the limit we saw in the preceding talk. Okay, but now here what I'm aiming at is a theory for problems where the macroscopic limit is diffusive. Okay, so as an extra assumption on the abstract level, I assume that this combination here is 0, which is translated to that the fluxes of the equilibrium distribution are equal to 0. Okay. Then you see this term goes away. The appropriate balance is now between these and these terms, so you have to choose alpha equal 2, the diffusive scaling. And now if you do the standard computations again, right, you can, if you just plug in these in the equation without multiplying by P, then you can get in the limit an equation for the R, which you need in the limiting conservation law, and writing it, what you get is this here. Okay. And the experts all know the appropriate steps, right? What you have to solve, you have to invert the collision operator in the computation, but actually the collision operator restricted. Of course, it doesn't have an inverse on the whole space, so you have to restrict it to the fluctuation part. Okay. So, and this is the limiting macroscopic equation actually. I want you to have a look at this operator here, because a very similar operator will come up in a minute. For the theory which I will do, I will simplify a little by basically dropping this inverse here in between, and actually not dropping it, but I mean it's a negative operator, replace it by minus the identity. Okay, and in actually the examples which I will talk about afterwards, this is actually exact. It is in this BGK model, this L hat operator is actually minus the identity. But for the method which I will present afterwards, I will always basically do as if it were minus identity. You will see in a certain sense. So I will talk a lot about this TP star TP operator, which is a kind of a caricature of the macroscopic diffusion operator. Okay, and now I'm ready to present the method, and it's actually embarrassingly simple in some way. All we do is to modify the entropy a little. You remember square root of the norm over 2, that was my original entropy, and now just I perturb it a little. I apologize for having epsilon. There's a black epsilon here, and I had a red epsilon before. The red epsilon was the Knudsen number, and the black epsilon doesn't have to do anything with it. It's just a new small parameter. Okay, so I just perturb the entropy a little, and the interesting thing here is this operator A. Okay, and you see already in this operator A that this TP star TP arises, which I had prepared you before, and then there is also a TP star, and you will see in a second what this is good for. The important part is actually the TP star here. And you can guess what this is good for. It's just good for making A bounded, more or less. Okay, it's a little bit, it's overdoing it a little, right? Because if you think about the point that T was a differentiation operator, what you see here, you differentiate once and you integrate twice. So it's overdoing the boundedness a little, but you will see that this is necessary. Okay. Now first of all, maybe let me jump first to this little lemma here, or to part of it. And part of this little lemma is to prove that this operator A is really bounded, as I said. It's not only bounded, it also just acts on the fluctuation part, which is also which will also be important later. And that is enough, of course, to make this entropy equivalent to the norm for epsilon small enough, the boundedness of A. Okay, so that is the first point here. So that this thing is actually is equivalent to the norm on the Hilbert space. Now you compute the time derivative of this H, and you get a whole number of terms. The first one is, of course, the good term from the H theorem. This is what we want to have. And the rest, the other terms, should help us with controlling the macroscopic part of the distribution function. And actually here, the good term will be this one. This is the one which controls the part of the macroscopic distribution function. You will see in a second why. And the rest is garbage. And you will see that the interesting thing is these first two terms. This is why the method works, and the work and the pain goes into the other three terms, controlling them. Because those two will provide control of f, and the rest you don't know about the sign and so on, so you will have to control them. So now, in the computations of trying to control them, you already see that you need this assumption here, which was my assumption that the macroscopic limit is diffusive. And you see that this is enough for two of these terms to be controlled. As I said, the operator A itself is bounded, but also the operator TA is bounded, right? Morally, it should be, of course, because as I said, you differentiate once, you integrate twice, now you differentiate once more, so that should be fine, okay? The interesting thing is that already on this abstract level, it can be shown that this operator is bounded, and with this we need here, okay? So that means there will be two bad terms still, which we have to deal with afterwards. But before that, I will talk about the good side of the story, okay? So now we'll make the essential assumptions which will lead to a spectral gap of the whole operator. The first one is what we call microscopic coercivity assumption. It's what I announced already, that the dissipation of the entropy actually controls the fluctuation part of the equilibrium distribution, the microscopic part. And we really need a spectral gap here, okay? You know, there's been a lot of work for different kinds of collision operators also recently, where in different situations, in particular for linearized Boltzmann collision operators, results like these have been proven, okay? So these is what we will need. The second is, as I said, is the macroscopic ingredient, what I call macroscopic coercivity. And it's written in this abstract framework in a simple form that when you apply the transport operator to the equilibrium distributions, that you get something which controls the equilibrium distributions. Okay? And actually when you rewrite this by using the scalar product here, and then you have TPF multiplied with itself, you changed one of the TPs to the other factor, right? And you have the TP star TP, which we had before, which was exactly our macroscopic operator. So this can be written as this is actually equivalent to saying that this macroscopic operator TP star TP has the spectral gap lambda m. Okay? And now if you look at the operator A again, I have to... what we just did is we combined it with TP, okay? So you have the TP star TP here, and the same operator here. So the spectral family of A is the same as the spectral family of this operator TP star TP, and so you immediately have you just can compute the spectral gap of this operator now, in this way. So that means this one term, which we had on the right-hand side, now does what I promised it would do. It controls the equilibrium part of the distribution function. Okay. And then we have two terms with trouble left, two operators, which one was this AT1 minus P, and the other one the A combined with the collision operator. And what we will need now is that both of them are bounded. And they're actually bounded in terms of the fluctuation part, but that's obvious because see, this one obviously only works on the fluctuation part, and the L also. So the fact that the big question is, are these two bounded? And now the interesting thing, for instance, here is that this one, as I said before, A is integrating once, T is differentiating, so morally this one should be bounded. But unfortunately, in the abstract setting, that cannot be proven in general. And you will see later why. There's a good reason for that. So it should be bounded morally, but at the abstract level, it has to be an assumption that it is. Okay, so it's not so clear, and we will talk about it afterwards, what it means. And of course, that's also an interesting assumption. A was bounded, so if L is bounded, it's done. So for the PGK problem. But later we will see there are examples of unbounded collision operators where this still holds. Okay. Well, and now the abstract theorem is if these assumptions hold, and the macroscopic limit is diffusive, then we have exponential decay. And I think you can believe. Let me go back to the entropy dissipation. Here you control the non-equilibrium part with a factor 1. Here the equilibrium part with a factor epsilon. And these terms can all be bounded by a product of non-equilibrium times f with the epsilon in front. So this whole thing is negative definite. Okay? So very simple. One thing which I forgot to mention before is that there was a motivation for this. And the motivation was in this paper by Hérault. On one of the examples which of the equations which I was looking at in the beginning, it was this relaxation model with for the Maxwellian case. And Hérault proved under certain assumptions exactly what we wanted to prove here by a method which is a bit more complicated. And our first idea was just simplify this method of Hérault, and I think this is much simpler than in the end than what he did. And it turned out also with a little bit of work that we could actually also improve the result in the sense that we will, I will show you later, need weaker assumptions on the confining potential than he does. Okay, so now applications. And the first application is embarrassingly simple, but it is nice to explain why things work at all. What's the underlying, say, geometry behind these, and so on. So I don't write the original example actually here. What I write is a trivial, about the simplest kinetic problem. You write in 1D a two-velocity model, velocity 1 minus 1, and no potential, because we put it on a bounded domain and we take periodic boundary conditions, so you don't need a confining potential. Okay, so this is the model, very simple. Now you do a Fourier analysis of that, expanded Fourier series, and then you see the problems decouple the Fourier problems, and they can be the individual Fourier problems are just 2x2 systems of ODEs. Okay, and this is what we get. So this is the problem after the Fourier analysis. You get a problem which looks exactly like my abstract problem, but now the Hilbert space is just R2, and so the operators are just 2x2 matrices, and the transport operator creates this skew-symmetric matrix where K is of course the Fourier variable, and the collision operator this simple matrix. Okay, so a very simple example. You obviously have microscopic coercivity with spectral gap 1, and if you do the computation, what means macroscopic coercivity here, you see that macroscopic coercivity means that K squared is bounded below, and since it's here in the natural numbers, it's bounded below by 1, so the macroscopic spectral gap is also 1. And the experts, of course, everybody notices that k squared is just a diffusion operator, right, in the Fourier space. So that this just this just the spectral gap of the diffusion equation with periodic boundary conditions. Okay. Now, in this case, our modified entropy function is the norm squared half as before, and this correction. Okay. And so you just add a mixed term and a little bit of k, because I want to basically, my problem is look at these for all k simultaneously, so I want results which are uniform in k at the end, and this is why I put this funny factor. Now, if you want to understand what's going on in this problem, it's very, very simple. I said some of the basic ideas are really very simple here. I don't find chalk. There. No. Where? The blackboard? Left on. Here. Thanks. Blind. So, just a little picture. R2. And what do the trajectories of this flow look like? The T turns, right? And the L contracts in the y direction. So the trajectories end up to be spirals. And actually what they look roughly like these. I have to be careful in drawing that. And the interesting thing here, and that the cause of all the trouble, is that the tangent is vertical here, right? So that when you draw circles, right, everywhere these spirals go inside circles, except these 2 points here where the tangents are vertical, and that's all the trouble. But since it's only these 2 points, and the important thing is if the turning is fast enough, or there is some turning, you're always driven out from here again by the turning, okay? And whenever you are away, you are contracted, okay? The contraction is in the vertical direction. That's all. It's very simple, okay? Now the question is just to provide a norm to overcome this problem, right? And provide a norm in R2 just means draw an ellipse, draw ellipses, a family of ellipses where this problem is gone. And actually you can get these ellipses by turning a little and turning a little in one way and contracting a little the circles, right? And then if you draw an ellipse, say something like, I forgot how to do it, basically like, no, I don't know. No. How do you have to do it? You have to, I think, yeah, it has to be like that, yeah. Suppose basically ellipses with an axis like this, right? And a little bit, so something like this, okay? Then you, that is what this modified entropy does, okay? And the bigger the k, the faster the turning, the more the trajectories look like circles, so the less you have to do, the less modification you have to do, okay? So that's the point here. So it's some way very simple. You compute the time derivative of h. You estimate uniformly in k, which is possible because of this form here. You get something like this, and you see for epsilon small enough, this is definite again, okay, like before. So that was the simplest problem, but it is a kinetic problem, although a very simple one. Now, what do we have to do if we apply this method to kinetic problems in a more general sense? So I want to look at a transport operator like I had it before with a confining potential. And first of all, I want to talk about these elements of the theory which do not depend on the details of the collision operator. That was actually a nice part. You remember my different operators, either they involved only the transport operator and the projection P, and only one of them basically involved also the collision operator L. So I can separate the two questions. So I look at the situation where the transport operator, as I said, is given by that, and the projection, and the projection is just, I said I want to have mass conservation. So I have an equilibrium distribution, a function of the total energy, and I want to multiply it by a function of x such that I have the same mass as F. So I have to divide it by its own density and multiply by its own mass and multiply with the mass of F. Okay, and for the Hilbert space, what I take is no surprise for the experts. You take the weighted L2 space where the weight is 1 over the equilibrium distribution. Okay, and since I have mass conservation, I can make it a vector space by asking that the total mass is equal to 0. Remember, in this, the F is a difference, has to be seen as a difference for the nonlinear problem between the distribution function and the equilibrium distribution. Okay. Now, first question, macroscopic coercivity. What does that mean? You remember this abstract macroscopic operator Tp star Tp as a spectral gap. I translate it to this situation. What you get is a Poincare inequality, basically. But it's a Poincare inequality with weights here. And the weights are actually are moments of the distribution function. So these I already had. This is the density of the equilibrium distribution function, and the MF is the energy of the equilibrium distribution function. So these things are actually, this rho F, MF are actually functions of the potential, of the confining potential. So that means you have a Poincare inequality with weights depending on the confining potential. Okay, and the details, of course, how they depend on the confining potential depends on the form of capital F. Okay, and we only need to consider those functions here where the total mass is 0. Actually, I have replaced the macroscopic density rho by u times rho F, so that this gets a nicer form. This is a symmetrizing transformation. Okay, so whenever you have to do an application, you want to do that, but everybody in the room here knows examples of that, I guess, for different choices of the weights. Now the second thing is, and that was deals with this operator AT1 minus P, where I said morally it should be bounded because it integrates twice and it differentiates twice. But the interesting thing, it depends a lot in which order you do that. And so there is this little lemma. What you have to do in order to prove boundedness of this is first solve an elliptic equation. And then, so given the W, I solve for this U here. Solve this elliptic equation, and afterwards prove a bound for the solution. And actually what you have to prove is that this equation regularizes in the typical way. So it regularizes from L2 to H2. Okay? So that's you have to prove. And so the equation is, there is this term which makes which always provides existence of a solution and uniqueness, right? So the inverse of this operator is upper bound in L2 by 1. But the interesting question here is this regularity of the solution. So you need to prove a regularity result. And what makes it not so trivial is that you need the regularity result in very particular weighted L2 spaces. So the Hessian has to be multiplied by a certain weight, the Hessian squared, and on the right-hand side also by a certain weight, which is natural here, right? So that's the natural weight here, and this weight here is actually now the fourth order moment of the equilibrium distribution function. Again, which can be computed as a function of the confining potential. Okay, and now this is actually the thing where most of the work goes in. The Poincare estimates, of course, if you start from 0, is also a lot of work, but a lot of this work has been done already, right? So Poincare estimates you prove by reading, but these will have to work by ourselves because these are not so standard results. This regularity. So now, special case of that The simplest special case of that, the Maxwellian case. In this case, all these weights which we had are just e to the minus potential. Okay. So what you need, so for instance, the macroscopic coercivity estimate is just the Poincare inequality with the weight e to the minus v. Okay. And now, as I said, you don't have to work for that. You read old papers, and for instance, this paper is actually about spectral gaps for certain Schrödinger operators, and the problem in this case can be actually translated to a spectral problem for a Schrödinger operator with the potential, with this potential basically. Okay, so if you rewrite it, and then you just need something, a result like this, which is a rather mild condition on the confining potential such that you have the macroscopic coercivity. The elliptic regularity estimate requires similar inequalities, or similar something related inequalities, but these, as I said, we had to work a lot to prove it. This edge to this is necessary for this L2 to H2 regularization, or necessary, we don't know, but sufficient. Okay, and again, rather mild conditions. What can I say? For instance, you can take a potential which, with algebraic growth, any kind of algebraic growth, which is, say, at least, yeah, bit more than linear, is enough to satisfy all these conditions. The interesting thing, I will say something about that before, is that the algebraic growth can be arbitrarily fast, which is from the applied point of view, or from it's natural, right? The faster the potential increases, the more confining it is, the better the situation should be. But this is not the same for all methods to prove something here. Okay, and now I can come to particular examples. So I take the Maxwellian case, and now two different choices of collision operators which provide the Maxwellian case. The first is the relaxation operator which I had before. As I said, if you take the Maxwellian case, the problem is linear from the beginning, so that it's not a nonlinear problem. And so we have this simple thing. And now we are basically done, because for this operator, microscopic coercivity is trivial, nothing to prove here, spectral gap 1. And the boundedness of AL is also trivial, because L is bounded and A is bounded, that A is bounded we showed before. Okay, so that is all the extra thing which we need from the collision operator here. The rest we've done on the previous slide. So we have reproduced the result by Hérault here, except that Hérault needed extra conditions on the potential. In particular, he needed boundedness of the Hessian. So that means he could only deal with cases where the potential grows at most quadratically, right? And as I said, we can allow for potentials growing much faster, even exponentially, and so on, and still get the result. The second application is interesting in the because it's an unbounded collision operator, the Fokker-Planck operator. So whenever you work in this business, you have to say something about this equation, because many people have done that. Okay. And here we are really lucky. Although it's an unbounded collision operator, if you combine it with A, it just looks like minus the identity. It looks very surprising, but to the computation, it's true. Okay, so that means that again, the boundedness of this AL is also trivial. A microscopic coercivity for this operator is again is the same as the macroscopic coercivity in X. It's just a Poincare inequality now in the V direction, and actually with a weight function, with a Maxwellian as weight function. So that's okay. Okay, and so we also have a result for this equation, and now we can compare to two previous works on this, and compared to Hérault, who did a big work, spectral analysis of that. We need weaker assumptions on the potential compared to work by Villani. He has very similar assumptions on the potential, but for the initial conditions, he needs H1, because he also constructs kind of a modified entropy functional, but that contains derivatives. Okay, so So we are a bit better in terms of what we require for initial conditions. And now finally, well, it's good. The last example, I want to show that although the method is linear, something can be done for nonlinear problems, but like always, when you apply a linear method to nonlinear problems, you need some very good control of the nonlinearity. So this is not, what I will tell you here is not the end of the story, hopefully, concerning nonlinear problems, because it's really it's a rather weak nonlinear result, as you'll see in a minute. What I need is that the initial datum is squeezed between two equilibrium solutions which are actually close. So we need, I need two equilibrium solutions where the parameters defining them, the quasi-Fermi potentials, as I would call them, are close. Okay? And the good thing in this case is that my simple collision operator, now, I was a little bit too fast. This is not for general gamma, it's for the gamma which leads to the fast diffusion limit. Okay, so this is what I wrote in the title here of the. So I take this particular example now, gammas which lead to the fast diffusion limit, and in this case, you can see that if you have this, then for the whole solution, the nonlinear collision operator is well approximated by the linear one. Okay, and that in the Hilbert space norm which I had before. So that is good enough to control the nonlinear terms, and you can basically just push the linear theory with a little bit more perturbations, and there's not much which happens. So the theorem is, you take a confining potential which has to grow at least quadratically, but not too much. In this case, we don't have, our result is not so strong comparing which potentials we allow, right? So yeah, quadratic at least, but not too much more. We don't know exactly what this beta naught of m is. And then we again get exponential decay, as I said, if we start close enough to a global equilibrium in this sense. Okay. Now here what needs to be said, the only thing I want to say is that for the macroscopic coercivity in this case, some people know very well what has to be done, like Adrien. What you need is Hardy-Poincaré inequalities. So these inequalities, Poincaré inequality, the macroscopic coercivity inequality, in this case is a Hardy-Poincaré inequality. And you need a lot more Hardy-Poincaré inequalities and a lot more painful work for getting this H2 regularization, which I talked about before. Okay, and now I come to the end. The good thing about this story is that it's a story which hopefully has a lot more to offer. So since the setting is very abstract in which we start, we can think about many different applications to it. For instance, systems of kinetic equations where, with reaction terms. So one of my interests recently is, like other people, is reaction kinetic systems compared to reaction diffusion. Try to do what's known for reaction diffusion also for reaction kinetic systems. And others do a Poisson coupling, so take a self-consistent potential. Some ideas on that. A big point is not only mass conservation, but other conservation laws. As long as the other conservation laws lead to a diffusive limit, that's in the framework of this. But as soon as you go out, you want to do Boltzmann momentum conservation, it's a different story, but there are ideas how to deal with that. There has been work by different people, but again, what we want to do is stay in a setting without regularity, and that has not been done yet. And then a third interesting question, we started some work with Vincent Calves on that, is what I call non-trivial equilibria. So it's equilibria which arise as a balance of the transport and the collision operator. So it's not equilibria which are in the intersection of the kernel of both, but which come up through the balance. so that one has to do something there. So that's also an interesting point for the future. And finally, I put the 2 references which exist so far on this, and thank you for your attention.